Welcome to the video lesson for section 3.4, solving exponential and logarithmic equations. Today we're going to put together all of our properties and use them to help us solve different equations. Let's get started. To begin with, ideally we want to try and establish one-to-one relationships for all of our equations. And what that would look like is if we have an exponential function, we have the same base on both sides, in which case we would just be solving for our exponents. If we had a log, we would see that we again have the same base. And then for our natural logs, we have a single natural log on both sides. So if we can set up these one-to-one relationships, then we have a very simple step from there to finish solving for our variables. Let's look at some examples. For our first example, we have 2 to the x is equal to 32. In order to solve this, we want to try and set up a one-to-one relationship. And what that means is, since I have an exponential expression on my left side, 2 to the x, I want to somehow rewrite 32 as an exponential expression as well, ideally with base 2. So that's our first step. We want to try and rewrite 32 as an exponential expression with the same base 2. Conveniently, 32 can be rewritten as 2 to the 5th. And now we have our one-to-one relationship. I have 2 to the x and I have 2 to the 5th. Since my bases are the same, my exponents must also be the same, so there isn't much solving left to do other than saying that x must equal 5 for these expressions to actually be equal. For our next example, again, we have some exponential expressions involved. We have 1/4 to the x is equal to 16. Now, generally speaking, fractions are not the easiest to use. So in the past with this chapter, we've rewritten that, and we're going to do that again right now. So instead of 1/4, what I'm going to have is 4 to the negative first power, and then I have my x, and that's going to equal 16. Now this should be a little bit easier for me to go ahead and rewrite both terms using the same base. I noticed that 16 is the same as 4 squared, so I can go ahead and rewrite that. And I'm also going to simplify 4 to the negative 1x. So we have 4 to the negative x is going to equal 4 to the second. Since the bases are now the same, the exponents have to be equal. And when I solve for x, we end up getting that it must be negative 2. We can verify this by plugging it back into our original expression to make sure we do in fact get 16, but that is it. All right, transitioning now to our natural logs. For our one-to-one relationship, we want to have a natural log on each side of our equation. And in this example, I have the natural log of 3 minus the natural log of x plus 24. So I'm going to go ahead and add the natural log of x plus 24 to the other side, which gives me the natural log of 3 equals the natural log of x plus 24. Since I now have a single natural log on both sides, my expressions must be the same. So 3 must equal x plus 24. I'm going to go ahead and write that down. And then to finish solving for this, if I subtract 24 on both sides, I end up getting negative 21 is equal to x. One thing we definitely want to double check, going back to the idea of our domain values, we cannot take the natural log of a negative value. So if I were to take my negative 21 and plug it in for my x value, does it give me a negative expression? And in this case, it doesn't. So I know for sure the answer is correct, and x equal to negative 21 is my final answer. All right, let's see how well this made sense. I want you guys to go ahead and pause the video and try and come up with the answer to each one of these on your own, and then check back in to see how you did. All right, so for our first example, again, we have some exponential expressions. I'm going to start by rewriting 49. So I have 7 to the x is equal to 49 to the negative first power. Then I want to try and rewrite 49 with the base of 7. Turns out that 49 is the same as 7 squared. So we have 7 to the x is equal to 7 to the negative second, which means that x equals negative 2 is my final answer. Similarly for number 2, I'm going to start by rewriting my 1/2 as 2 to the negative first, which means I have 2 to the negative x, and that equals 32. If we look back at one of our previous examples, we knew 32 is 2 to the 5th. So then I have 2 to the negative x is equal to 2 to the 5th, which means that x must equal negative 5 as our final answer. And for our final answer, our first step would be to go ahead and to move natural log of 9 to the other side. So we would have natural log of x equals natural log of 9. Since we now have a one-to-one relationship, we can go ahead and cancel our logs, and we would just be left with our answer of x is equal to 9. All right, our inverse properties. These are used when we can't set up a one-to-one relationship, but we can use inverses to help us eliminate or cancel out part of our expression. So just to remind you, a to log base a of x is equal to x. Again, the a and the log base a are going to cancel, and we're left with just our value. Also, log base a of a to the x is equal to x. Here we can see if the base and if both bases are the same, they cancel out, and we get just the exponent as our answer. And then for our natural log, or e to the natural log of x simplifies to be just x, and the natural log of e to the x is going to be just x as well. So again, what we're going to do is we're going to introduce these properties when we can't set up a one-to-one relationship, but we can use inverses to cancel something out. Let's take a look at a couple examples. All right, so we have the natural log of x is equal to 6. If you think about doing our one-to-one relationships, I need to see a natural log on both sides, and I can't do that because there's only one natural log. So what I'm going to do instead is think about inverses. I know that e is the inverse of the natural log. So thinking back to my properties, if I could raise up the natural log as an exponent, I can then get it to cancel out with e. And so that's our first step. I'm going to rewrite this whole thing as e to the natural log of x is equal to e to the 6th. So now the natural log of x is an exponent and 6 is an exponent. Conveniently, we do this because the natural log and e are going to cancel out as inverses, and my left side will simplify to be just x. And on the right side, I get e to the 6th, and I'm done. Final answer. All right, for our next example, again, we can't establish a one-to-one relationship, so we have to think of how do we cancel things out. And the way I can cancel a log is by using exponential expressions. I want to take that log and again raise it up as an exponent, and my base for this one is 4. So I'm going to use 4 as my base for my exponential expression as well. And what that means is I'm going to rewrite this as 4 to the log base 4 of x, and that's going to equal 4 to the 2nd. So again, what we do on one side, we have to do to the other side as well. Looking at our inverse properties, 4 log base 4 of x is going to cancel out because they are inverses. My left side is going to simplify to be just x. And on the right side, we have 4 squared. And we can go ahead and simplify that to be 16, and we have our final answer. Our last two examples had a log or a natural log, and we saw the process there was to raise them up as an exponent to get them to cancel out. For this example, we start off with an exponential expression. So what we're going to do here is we have to again think what cancels out with e. And in this case, it's going to be the natural log. So I'm going to take the natural log of both sides. So I have the natural log of e to the 2x is going to equal the natural log of 4. The reason why we do this, thinking of our inverse properties, the natural log of e is going to cancel out because they're inverses, and I'm going to be left with just my exponent. So my left side is going to simplify to be just 2x, and my right side is going to be the natural log of 4. And then for my last step, I'm going to divide both sides by 2, and I get x is equal to the natural log of 4 divided by 2. And that is my final answer. All right, this time we're going to go ahead and use logs. And when I use logs, I want to make sure my base is the same as the base for my exponential expression. So right now my base is 3, which means when I take the log of both sides, I'll be using the same base. So we're going to start with that. I have log base 3 of 3 to the 2x equals log base 3 of 9. Using my properties, I can use my exponent and move it to the front. So I have 2x log base 3 of 3. And I'm also going to rewrite 9 as 3 squared. So I'm going to do a couple things here to kind of simplify. I can deal with my log base 3 of 3 over on the left here. And on the right, I can do the same thing. We know log base 3 of 3 will cancel, and it'll leave me with basically my exponent. So when I simplify this one more time, what I end up getting is 2x is equal to 2. And then I have to divide both sides by x. By 2. We get that x is equal to 1. My personal preference when solving these type of problems is to always begin with the natural log because I don't have to worry about what the base is, and it will work for every exponential expression as long as you do it correctly. So my first step would then be to take the natural log of both sides. So we have the natural log of 3 to the 2x is going to equal the natural log of 9. I can then go ahead and move the exponent out to the front. In this case, though, I'm just going to go ahead and move the x out to the very front. So what I have now is I have x times the natural log of 3 squared, and that equals the natural log of 9. 3 squared is 9, so I'm going to go ahead and simplify that. So we have natural log of 9 equals natural log of 9. And then if I divide both sides by the natural log of 9, we once again get x is equal to 1. Now again, this is my personal favorite, not because it's the most efficient or the most effective, but it will always work. You don't have to worry about what specific base is because natural log just kind of take care of itself. But we have one more way to solve this problem to compare our three processes. All right, for our third process here, we're going to go ahead and use a one-to-one relationship. Now, for this problem specifically, we can. You are not always able to, so that's where you would use the log or the natural log process. But in this case, we can because I can rewrite 9 as a base of 3. So I can start off with 3 to the 2x is going to equal to 3 to the second. Because my bases are the same, my exponents must be the same, which is the one-to-one relationship there. And if I solve this, again, I'm going to get x equals to 1 as I did for the other two processes. Now in this specific example, using the one relationship was nice and easy. And if you see that you can rewrite 9 as 3 squared, then you can go that process. However, again, I prefer to use the natural log because it always works. You don't have to worry about bases being the same. You can just always get through and get to your final answer without having to, again, make sure your bases are in fact the same. All right, guys, I want to test yourself here. Go ahead and pause the video and see if you can identify the correct answer for these three, and then check back in and see how you did. Okay, for our first problem here, we're going to go ahead and rewrite it as an exponent. So I'm going to say 7 to the log base 7 of x is equal to 7 to the negative third. The reason why we do that is to get our log to cancel out. So this process gets rid of that, and we end up just getting x is equal to 7 to the negative third. For our next problem, threw a little bit of a curveball here because our base is an x value, and you can't really just say x log x because everything will cancel out. So what I'm going to do instead is I'm going to go ahead and rewrite this as x to the fifth is equal to 243. And then I could take the fifth root of both sides, and if you take the fifth root of 243, you get 3. All right, for our final equation here, we're going to go ahead and start by taking the natural log of both sides. So I would have the natural log of e to the 2x equals the natural log of 5. I can get my natural log and my e portions to cancel out because they are inverses. So these will cancel, and I'm left with just the 2x is equal to natural log of 5. And then if I divide both sides by 2, we get our final answer of x is equal to the natural log of 5 divided by 2. All right, we're going to make things slightly more challenging here. We want to try and get the natural log or the exponential expression by itself for these. In this specific example, we see we do have a natural log of x. So I need to get that by itself before I can begin to do the steps we did in our previous examples, which means I'm going to start by subtracting 3 on both sides, which gives me 2 times the natural log of x is equal to 8. Then I'll divide by 2. So now I have the natural log of x is equal to 4. And because I have the natural log, I know I need to bring in my e to try and get it to cancel out as an inverse. I also know that I can't use my one-to-one relationship because I only have one natural log. So I'm going to raise up both these as exponents, which means I have e to the natural log of x is going to equal e to the fourth. The e and the natural log being inverses will cancel out, so I'm left with x on my left side, and it's going to equal just e to the fourth, and that is my final answer. Okay, similar process here. I need to try and get my log by itself. So I'm going to go ahead and move everything to the other side. I'll start by dividing by 4, which gets me log base 10 of x minus 6 is equal to 3. I need to get the log to cancel out. So as I did with my natural log, I'm going to raise it up as an exponent using 10 as my base because that was my base for the log, which means I also have on the other side 10 to the third. The 10 log base 10 will cancel out because they're inverses, and I'm left with x minus 6 is going to equal to 10 to the third, which is 1,000. And then if I go ahead and add 6 to both sides, I get my final answer of 1,006 for x. All right, so here what we're going to do is start by condensing the logs on one side because we need to always have a single log before we can try and solve these. And notice that we're adding our 2 logs, so if I condense them, that means I would be multiplying my expressions together. So I have log base 3 of x times x minus 8 is equal to 2. I want to go ahead and get the log to go away. So the way I'm going to do that is by raising it up as an exponent, and I will use my base here to become the base for my exponential expression. So I'm going to have 3 to log base 3 of x times x minus 8, which means I have to do it on the same, or do the same thing on the other side, which would give me 3 squared. All right, so we do this to get this portion to cancel out. So what I'm going to be left with is x times x minus 8, and then that's going to equal 3 squared. I'm going to simplify here to get x squared minus 8x is equal to 9. Continuing to solve this, I'm going to subtract 9 on both sides. So we have x squared minus 8x minus 9 is equal to 0. And then I'm going to go ahead and factor this, x minus 9 and x plus 1. And if I solve this, we end up getting two values, x is equal to 9 and x is equal to negative 1. But we always have to check our values to make sure they work with the original expression. And we do have a problem here. If I try and take this negative 1 and plug it into this expression, I get log base 3 of negative 1. And we can't actually evaluate logs of negative values, which means this is not an actual solution. And our only solution to this problem is x is equal to 9. Okay, we have a similar problem here where we have two logs on one side. We want to condense to be a single log. This time we're subtracting the two. So when we condense them, we're going to divide the two expressions, which would give us the natural log of x plus 1 over x minus 2, and that equals the natural log of x. Since we have a natural log on both sides, we have a one-to-one relationship, so I can go ahead and basically drop those natural logs. It will cancel off. So I have x plus 1 over x minus 2 is equal to x. And I'm going to go ahead and write this x over 1. And the reason I'm doing that is I'm going to cross multiply. So we have x plus 1 over x minus 2, and that equals x over 1. And I'm going to cross multiply to go ahead and start solving this, which gives me x plus 1 equals x squared minus 2x. And then I want to subtract my x plus 1 to get it equal to 0, which gets me x squared minus 3x minus 1. I would have to go ahead and try and factor this. It doesn't factor very easily, so we can use our quadratic formula that we learned in the last chapter. And when I solve this, I end up getting two values, x equals 3.3 or negative 0.3. And it turns out that this negative 3.3, if you plug it in, doesn't actually work, because if you plug it into our expression, either natural log of x minus 2 or natural log of x, we get a negative value. So we're going to cross that one off and keep just 3.3. All right, that does it for the notes. Go ahead and get started on the homework, and good luck.